When we're looking at first order differential equations, we can actually use something called the Uniqueness Existence Theorem to prove in which regions of the plane that a unique answer will actually exist. So what do I mean by that? If we have a first order differential equation, that just means the highest degree is 1, means we should be able to get that derivative all by itself, and on the other side you'd end up with a function of the independent variable x and the dependent variable y, some function on that side. Well, this theorem states that you will have a unique solution everywhere f of x and y and the partial of f with respect to y are defined. Now, this is a spot where you may not have seen this before. This means the derivative with respect to y or the partial derivative with respect to y. If you're not familiar with partial derivatives, go ahead and stop this right now and go watch a video on partial derivatives. There should be one posted for you so you can understand how we're doing this, and then come on back and pick this up right here. So, as long as we have a first order differential equation and we can isolate that derivative, then we can actually guarantee which regions of the plane that we should have a unique solution. Now, unique's important because you want to know that the answer you got is the only one possible, so you know that your answers only apply to your situation. So let's take a look at a very simple one. Let's say if I said something like y prime is equal to x times the let's do the fourth root of y, something horrible. The fourth root of y. And the question would be, where are you guaranteed a unique solution? So where would we be guaranteed a unique solution? So right here, this is our function of x and y. The derivative is already isolated. So this is x times the fourth root of y. So we need to look at this expression, and we also need to figure out what f sub y is equal to. Well, remember, this is x times y to the 1/4 power. So the derivative of this with respect to y, remember, x is a constant, so we bring down the power and take 1 away from the power. That's negative 3/4. So another way to write that, if you wanted to, that would be x over 4 times the fourth root of x cubed. Oh, y cubed, sorry. All right, so there's our function and there's our derivative with respect to y. So let's start out with our function. Where is this defined? Well, in this course, we're mainly, not completely, but mainly going to stick with the real numbers. So since this is an even root, this implies that the stuff inside here has to be greater than or equal to 0. So from here, we can see y has to be greater than or equal to 0. Now, and that's the only restrictions on this one. If we look at this here, we still have the same restriction on y because it's inside the radical, but now we also say that y can't be 0, so y just has to be strictly greater than 0. So if we take a look at this differential equation and we look at the plane, now we got to take the most restrictive case of these two. So by combining these two, you see that the region that we were guaranteed a solution is what? Just where y is greater than 0. So I'm going to put a dotted line on the x-axis, and this would be the region up there. So if we had this problem here, and we had some initial value for it, we would have the unique solution for any initial value in that first quadrant, or in the first and second quadrant, not including the x-axis. So this is pretty powerful. We actually don't use it a lot, but it's very, very quick and easy to do. Anywhere that the function is defined, and anywhere that the partial with respect to y is defined, take the combination of those two, and that will tell you where in the xy plane you're guaranteed a solution. All right. So let's try another one here. What if I said y dx is equal to the natural log of xy? So again, by definition, here's our f of x and y is the natural log of xy. All right, we also need f sub y. So the derivative of this with respect to y. So the derivative of a logarithm is 1 over the argument times the derivative of that argument. Now we're taking the derivative with respect to y. So the x is a constant, just like if it was 7y, the derivative of that would just be 7. So the derivative of xy is just x. Okay, so simplifying this, f sub y is just 1 over y. Okay, so what can we say about this region? Well, from the first one, this will be defined. Remember, we're never allowed to take the log of 0, so we know that that can't be 0. And we don't want complex numbers, so that stuff inside there can't be negative. So we need that x times y just has to be strictly greater than 0. It's not allowed to be 0. And down here, we can see that y cannot be 0. Okay, so what regions are we talking about here? So this one's going to take a little bit more thinking if we're thinking about our xy plane. Well, x times y has to be greater than 0 or positive. It also means that what? X and y cannot be 0 because then it won't be true. So here, here's where y is equal to 0, so we know we can't have the x-axis. Here's where x is equal to 0, so we know we can't have the y-axis. Now, for x times y to be greater than 0, it has to be positive. So they either have to both be positive or both be negative. So they're both positive in the first quadrant, and they're both positive in the third quadrant. So you can see from here, as long as we have an initial condition in the first and third quadrant, excluding the axes, then we should have a unique solution to this differential equation. All right, so the only problem for a lot of people is the partial derivatives. Like I said, go check a video out if you're not sure how to do that.